I like to repeat a little bit. Like, I mean, I spent like last 20 minutes last time to talk about kernel PCA. I guess it's really rushing it. So I like to spend at least a little bit of time. Maybe actually even go through a little bit like PCA. I mean, so I don't know how yeah, hopefully it's not totally useless to you guys. I guess maybe it's a revision for some of you guys, linear algebra, and for me also. So so to begin with, like if you remember the PCA, so we kind of course the first thing we need to take advantage the eigenvalues and eigenvectors, right? Maybe just a quick note like what's eigenvalue, eigenvectors. Now I see, hopefully it's not, okay, I'm using wrong pen. So remember I have a matrix, then eigenvectors will be just if maybe I have eigenvector V, I multiply by C will give me like lambda and V, right? So now if I have, for this matrix is n by n, so then I should be able to find, actually it's not always, but if this is symmetric, then I can always find eigenvectors, complete eigenvectors bases like V1 up to Vn. Maybe I use big N here. So then like I have CVI, all of them is just equal to lambda VI, lambda IVI, right? So then I can write C V1, V2, and so on is equal to lambda 1 V1, and so on up to lambda n Vn, right? And then I can rewrite this as a V1 up to Vn. Actually, I can write more on this side. So each of these eigenvector is n by 1, right? It's like a column vectors. So because the matrix is n by n, so this is like n by 1, right? N by 1. So I have n of them. So this is actually, I pack all the eigenvectors together. This is an n by n matrix, right? This is also n by n matrix. Now I can rearrange this like lambda V1, lambda and so on. I can write like this, right? Does it make sense? Right. Yeah. So then like this is also like same thing. Maybe I call big V here. I mean both of them call big V here. So then you can see that I have CV V inverse is equal to this lambda. This is diagonal matrix lambda here. Right. So I can basically, the eigenvector will diagonalize a matrix. I assume C is symmetric matrix basically. And if symmetric also, like I won't show it, but you can show that like you can find eigenvector that are orthogonal and normalized in the sense that like I have Vi, Vj, so the inner product, or like this would be like Vi transpose Vj will be just equal to 0 if I is not equal to j or equal to 1 otherwise. So it's a normalized eigenvector. So if so, then basically V is a so-called orthogonal matrix, right? Orthogonal in the sense like if I think of like V transpose multiplied by V, for example, then what is that? This will be, so in terms of like, because this V is a bunch of V1 vector eigenvectors, so V1 to Vn, and this is a V transpose, will be like V1 transpose and Vn transpose. So this multiplied by that will be like V1 transpose V1, right? V1 transpose V2, and so on and so forth. And this is a V2 transpose V1, V2 transpose V2, and so on and so forth, so on, right? And from what we just mentioned, that like the eigenvectors are orthogonal, best orthonormal basically is like both orthogonal and also normalized. So this the diagonal elements will be all equal to 1, right? And the off diagonal will be all equal to 0. So therefore, like, I have this matrix, I will have V transpose V is just equal to identity. So this is like basically a definition to be like orthogonal matrix. So the nice thing of orthogonal matrix, I'm not sure if you realize that or not. If you think of that as a transform, an orthogonal matrix applied to any vector is just a rotation in the space. Include mirroring, like you can also have rotation and mirror. So basically, the distance between, 2 points before and after the transform will not change. So I can easily show that. For example, if I consider a vector x, so if I transform that, like I have Vx, kind of like apply this orthogonal transform to x. So and I look at the norm of that. So the norm of that will be Vx transpose times Vx, right? And the norm of that, basically the square distance of that vector will be just x transpose V transpose Vx. Or I can write here Vx square, right? So then because this is identity, it's just x transpose x is just x squared. So as I said, it doesn't change the distance of that vector. So let's see, do I have everything for what I need to introduce? Okay, now I said C, right? What is C actually I'm interested in? What I'm interested in is, like, if I have some random variables. So I have our space here. So I guess I'll just this is the main thing, right? I can, if I have symmetry matrix, I can diagonalize with this V, and V is just eigenvectors. Now if I consider now C in particular, I pick C as the covariance matrix. So I have random variables like x here is a random multivariate random variable, so have an element here, x1 up to xn, I say. Now, then if I assume this zero mean, so like I just make it easy, I assume this is always zero mean. It means that expectation x is just equal to 0, so just a 0 vector. So then the covariance matrix is what? So can anyone tell me what's the covariance matrix for so or maybe I start asking, like, just look at one variable here, x1. What's the variance of x1 in terms of expectation? So the variance is, if you remember, variance is measured the square distance from the mean, right? So basically, if you have variable x, let's say this is scalar variables, maybe I use x1 here. I have just pick the first element x1 here. The variance is like expectation x1, the mean multiply, subtract the mean, right? Subtract the mean and take the square difference. I look at the expectation of that, right? If I assume that it's already zero means, then I can simplify that just to be x1 squared. Just make things a little bit simpler. Right? So this is basically the variance for, I guess often people will just write sigma 1 square, right? Sometimes you see sigma 1 square is just equal to that if I assume zero mean. Now, how about if I have a vector variable? Then the covariance matrix, what's the covariance matrix is basically is something like the expectation, a matrix of expectation x1, x1. That's basically the variance here. Or I can write, yeah, let's write this, right, make it simple. x1 square, because I also zoom in here, and the expectation x1, x2, expectation x1, x3, and so on. And the second will be expectation x2, x1, expectation x2 square. This will be the coherence matrix. And then if you look at that in terms of vector form, it will be, I can simply write this as x transpose, right? If I have like x is this one, right? X is a vector variables, then this matrix is just equal to this vector is n by 1 multiply this transpose here is 1 by n. Then you multiply the whole thing out, will be like this way. But the expectation can apply when you have an expectation to a matrix. Essentially, your expectation apply into each of the individual elements in the matrix. So therefore, like the coherence matrix is just equal to this. So any question for that? Okay, please ask any question. I don't think like any question for that. I mean, like don't worry about that. Like I understand like sometimes this will get rusty, especially people in graduate school, honestly. Typically, when you're doing undergraduate, the things you just study like in this semester, so you get pretty much. Any question? And by the way, like I can't help to kind of like digress a little bit to mention a kind of inner product and Cauchy-Squash inequality here. If you think of like what is this expectation x2, x1, actually of course it seems like a little bit what I say what's that word, tautology, or like this one I say just for simplicity I call it sigma 1 square, this is the sigma 2 square, and so on. This one I can write as rho 1, 2, sorry, sigma 1, sigma 2. Okay, of course you will say like what's the use for that if I write this rho 1 to sigma 1, sigma 2, and this I may write rho 1, 3, sigma 1, sigma 3. But this rho 1, 2 or something is actually the correlation coefficient. That has to be in a range from -1 to 1. So it's something like, in other words, you should have like expectation x1, x2 is okay, what I say is equal to rho 1, 2, sigma 1, sigma 2, right? So and if I put a square here, okay, I put a square here, rho 1, 2 square, sigma 1 square, sigma 2 square. So I have like equal to rho 1, 2 square. Okay, just like sigma 1 square, sigma 2 square. So, but then like you look at rho 1, 2 square is equal to expectation x1, 2 square over sigma 1 square, sigma 2 square. So I'm claiming this one will be less than equal to 1 basically. So if this is less than equal to 1, then I can make sure this correlation coefficient is bounded by bounded from -1 to 1. Physically, like what does this mean is like when you have like correlation coefficient is equal to 0, then the two variables are not correlated. And if I have like x1, I mean this ρ12 is equal to 1, they are correlated to the maximum. So in the sense, actually that essentially implies that they are identical. Basically, one variable is just a scale value of the other variable. And if you have opposite -1, it's like it's minus of each other. So maybe x2 is equal to minus some a times x1, where a is positive, some positive number. So this is very tempting, like for me to show this thing actually. This because it's so neat. I think like this is like you can essentially, if you remember, there's a Cauchy squash. Oh, I'm not sure how to spell it. Yeah, I think it's like that. Squash inequality. That. See any? I think you think, right? I think especially you did the math minor. I think you should have seen that. So but that is like okay. There are many forms of that, but most general form is just like if you consider two inner products. If you define inner product, I'll say what I will say like what I define inner product later on. You define inner product, then like I have in some whatever you call vector space, but don't be worried about like space, like don't need to be abstract. But I have something I call it an inner product that x y will be bigger than equal to xy squared. So something like that. And the beauty here is like the inner product can be anything. So you see, like for example, in vectors, you probably see that like in vector space you define two vectors, like let's say x, again like some column vector n by 1 and y another column vector. So I can define this inner product just as like what we did earlier, that maybe it's x transpose y, like kind of like a dot product between them. But here I can also define inner product that I will define like if I have some random variable x and random variable y, I define the inner product xy simply as the expectation xy. And of course, okay, how can I make sure this is something valid? So I just need to show several things. I want to make sure that like it's linear, something like if I have x1 plus x2 y, then I will have hopefully I will have like x1 y plus x2 y. And of course here is very easy to show it definitely very easy to show x1 plus x2 y. So because the expectation is linear, so therefore it's a x1 y plus x2 y. So therefore like this whole. And I want to also show, for example, like it's, if I want to show it to be linear, then I better also show like x y, let's say ay is equal to axy. So again, it's obvious. If you just pop into that, it's obvious. So another very important is I want to have like x is bigger than equal to 0. And again, this is obvious because I have this is just equal to expectation x squared is equal to 0. Now the nice thing is I just need this kind of property, whatever. I mean, I don't need to care about like how I actually define this inner product, but I only have this property. I can show that this inequality hold. One very easy way to show is I can that's complex inner product, but here I just focus on real. The proof of real I think is easier. So let's say I consider x plus ay and x plus ay, and by the property I have here, this is bigger than equal to 0, right? So, but by this linear property, I can expand that. This will get like x, and maybe I just go step by step. X plus ay x plus ay, let's say something like that. And of course my a can pull out, right? So, and then like I can go one more step here, will be like x plus ayx plus axy plus a square y, oops, plus a square y. So this I can put together. This is 2axy. Now then what I have here, this is bigger than equal to 0. I'm saying like this guy must be bigger than equal to 0, right? Now this is a quadratic equation, right, in terms of a. So this is always bigger than equal to 0. It means that I have something, a quadratic equation, always above that. And if you remember from high school, so if you have a quadratic equation, the solution for the quadratic equation, like a will be have some value like minus 2. Do you guys still remember? Minus 2. I guess it's a minus yx, and this is 2yx plus minus okay, I remember. Yeah, I need to write this first because otherwise okay, this is I assume this is basically if I have x squared plus ax squared plus bx plus c, right, something like that. So okay, let's look at that. So I have b is this guy, right, and plus b squared is like 4xy squared, right, and then minus 4xx and yy, right, because this is a, this is c, right, 4ac, and over 2 whatever, 2, I don't care that part. The main thing is this part here, right, because here I'm saying that this has to be bigger than equal to 0. It means that I can only have one solution, right, at most, right? So this means that this one has to be negative, right? If I have positive values, then this will be have like two real solutions. Yeah.
So for this equation, the a is the unknown one. So
yeah.
So a squared, yy is a.
Yy is a. Yeah, yy is a.
So you use the formula.
I use the formula. Yeah. Yeah, I get yeah, this is 2a here, but yeah, but better not to use a, but yeah, I did it anyway. Yeah. So okay, so but as I said, like here the cool thing is that you look at this, right? You can only have one solution, right? At most one solution. It means that this cannot be positive, right? So if the value inside this square root is positive, I will have two solutions. So therefore, I must have like xy squared minus xx yy is less than equal to 0. And that's precisely this thing here. And then I use this cross inequality, then immediately I get this, right? I have this is defined the inner product is a x squared, expectation y squared is bigger than equal to expectation xy squared, something like that. So therefore, like I have rho square must be less than equal to 1. So okay, that's some sidetrack for probability thing. Yeah, but I think this is very cool. I mean, I remember I talked in a presentation that in undergrad, it's like some kind of like just a course about like trying to give presentation. I talk about this because I think it's very cool. So let's see. Now I guess now let's go to. I have this coherence matrix. Remember, I defined this coherence matrix now. Is sigma 1 square, sigma 2 square, something like that, sigma n square, and each of these diagonal terms is sigma 1, 2, sigma 1, sigma 2, and so on and so forth. Right? I have maybe the kj1 will be like rho k, rho ij, maybe sigma I, sigma j, stuff like that. Now, if I look at a special case if I all the variables are independent, not uncorrelated, so like rho ij are all equal to 0, then I will have a diagonal matrix, right? C will be a diagonal matrix. Then along each of the axes, like this diagonal is just the variance, right? So, and in that case, if maybe I consider 2D here, let's say I have like n equal to 2, what will I have will be have something like that. So I have points, maybe this is samples like that. So, and this is like, let's say along this axis is like for sigma 1, and this will be like sigma 2. So essentially this or maybe I should say x1, x2. I shouldn't say sigma 1, sigma 1. This is like x1 and this is x2. So then like the basically sigma 1 square is the variance along this direction, right? So it's like just how this data point is spread along this direction. And sigma 2 square is like how this data point is spread along this vertical direction here. And let me give another example. Let's say if I have also like 2D, if my rho 1, 2 is not equal to 0, what do I get? Or like if I rho 1, 2 equal to 1, or close to 1, maybe I'm showing like close to 1. So what I have will be basically like this. So when you are so you can see if you have data point here, like along this axis, basically saying that if I have one point is big, one component is big, x1 is big, x2 will be big as well, right? At the same time. That's what we mean by correlated, right? But here, like you see, like for this point here, like when they are not correlated, I given like x1 is like in whatever location here. Actually, it doesn't give me some extra information for me to estimate x2, right? Because I'm here, I say x1 is here. I'm still not sure whether it's a where location, right, for x2 here. Maybe I want this here, but I don't know where is it. And if x1 is here, I still have no idea. It's probably around here, but I don't know where is it. But on the other hand, when I'm correlated, if x1 is here, it gives me some extra idea. Okay, x2 has to be in this range, right? But if like I have x1 is like somewhere here, then x2 better in this range. So any question? Okay. Now I want to. What is interesting is I want to know like this direction here. What's this direction here? And what's this direction here? Say.
Eigenvectors.
Yes. These are the eigenvectors. Why they are the eigenvectors? Let's see. So let's say Let's see. Let's say like I focus on the biggest spread here, like the direction that is have the maximum spread. So I can formulate this problem. If I want to figure out what's that direction here, I can formulate this problem as follow. So I want to say, okay, I have this random variable like x, again, like a vector random variable. Now I project it along this direction here. I think I kind of like overload the simple a, but I'm using a in this node, and let me use a again. So then if I project in that direction, basically I will have a transpose x, right? And of course I want this to be a projection, so I better to have a is like have a is normalized, the norm is equal to 1. So if I want to find the biggest spread there, so essentially I want to find the one have maximum. Maximum projection, probably trash. I think it should be trash. So right, something like this, right? So, but then this guy, I can write this as this is a write this as let's see, a transpose. Yeah, I can write like this: a transpose x, x transpose a, right? Let's see. And of course, if I write like this, then this will become like a transpose. My expectation can get inside, so x transpose a. So that will just give me back the coherence matrix, right? Now, if I because I have a is normalized, right? I can kind of decompose A with the normalized eigenvectors there. So the eigenvectors of C there. So we remember that let's say the eigenvector of C is just V1 up to Vn, and they are normalized. So I can have A defined as W1 V1 plus W2 V2 and so on to Wn Vn. So then if I do that, so and you see. Oh, okay. So then if I do that, let me just substitute inside. Let's see, a so let me write the summation form here. I have W I V I transpose multiplied by this C here on the left, let's say, and then I on the right I use another W index. I say J W J V J, something like that. And but if I C multiplied by Vj, I have lambda Vj, right? Because they are eigenvector, so I have lambda j Vj Wj, sum over j. Actually, my summation all pull out, so I have summation I and j. I have Wi and Vi transpose here. Basically, I will have something like that. But of course, like Vi and Vj, Ij are kind of orthogonal to each other. Like they are kind of I mean, they are only, the inner product is only equal to 1 when they are identical, so I have essentially a delta function here, delta ij, right? And wj lambda j wi sum over ij. So eventually I have sum over I wi square lambda I, right? And because A is kind of normalized to 1, right? So I should have this weight kind of sum up to the square should sum up to 1 as well. And then if you look at that, like when is this biggest? I don't know. What is that? What? Oh, okay. I see why I keep receiving this. Okay, it's a winter storm like tomorrow, so it's only Tulsa. Okay. Oh, okay. So.
Could you remind us, this sort of stuff? Like, can you remind me, like, what is eigenvector? I kind of forgot the concept.
Yeah, eigenvector is going back to here. Eigenvector is this way.
Yeah.
So you have an eigenvector. You have a matrix.
Yes.
Actually, it's better to assume this is a symmetric matrix. So a matrix multiplied with eigenvector is equal to a eigenvector multiplied by vector. But I guess the most important thing is that if you pack all the eigenvectors together, you can form an eigenvector matrix like this, right? Like V1, V2 up to Vn. And then like if C is a symmetric matrix, there's a very nice property that like you can find eigenvectors. They a complete set of eigenvector, they form a basis of a normal basis. So the eigenvector are kind of normalized and orthogonal to each other.
How this concept related to
Say that again?
like, how this concept related with the different, like.
Oh, okay. This is I'm related to, I guess, more statistics or something. But okay. We were talking about kernel PCA. I'm thinking like, okay, maybe I just quickly like going back to just even so, but then like this guy at the end now, then I will essentially, if I will, let's say the lambda sorted, so if I want to get the maximum one, then I should just pick like that. For example, if I sorted like in a descending order, like the lambda 1 is bigger than equal to lambda 2 and so on and so forth. So in order to maximize that, I should just pick W1 equal to 1 and then the rest is equal to 0, right? So therefore, like this essentially means that like the maximum along that direction is just the eigenvector, as Robbie said there. So let's go back to now what we talk about. Kernel PCA, just a quick. Let's see. I'm already inside. So actually what we mentioned last time is that so for the kernel PCA is like we want to utilize the kernel trick, so we project to like higher dimension, right? So we have a higher dimension instead of the original dimension x. We will project to find phi x there, phi x there. So therefore, your covariance matrix become this way, just what we have earlier, right? So, okay, I have a summation here because instead of expectation, here I assume I have like n data point here, and I use that to approximate the covariance matrix. But the key here is like I don't actually know the phi here. I don't know the phi here. So, and supposing you project to high dimension, I'm not able to compute this. But actually, I can assume that I'm able to compute this instead. So this is always like what we have for kernel trick. So it's like we will assume that we are able to compute this, something like the inner product like of phi x and phi y, and this will become some kernel function there. So then we want to find again, like just like PCA, we want to find the eigenvectors of this matrix, right? But it's not, we don't know how to do that. But we mentioned last time that it turns out if you have the training data that, as I mentioned again, it's like x1 up to xn, the eigenvectors will be just a weighted sum of this like phi x. It's a linear combination of this phi x, and it's very easy to show that. I won't repeat it again. And but still, like, okay, then okay, with this, then we can substitute this back to here, right, and try to figure out if we are able to solve this eigenvector here, because even though we know the form is here, we still need to figure out what's alpha, right? So if we substitute that back, and if we go for some algebra, let's see. So basically, like we still have CV equal to lambda v, right? So v, as you mentioned, is this guy here, right? So this is v here. So C is this one here, and V is this one here. So I just changed the order of this summation a little bit. Then what you find is that this guy is actually essentially the kernel matrix. Not the kernel matrix, but this is like computing, is essentially a kernel function, right? So this is something I can compute. But I still have this, it's not good. I don't know how to compute. But I can try to do the same thing. I can multiply both sides by some phi transpose here. So if I multiply phi transpose on both sides, then I will have something like, similarly, we'll have some kind of kernel function that I probably can able to compute. So if I do that, I will have, it's hard to see, so I have this guy here. I will call this like, the kernel matrix is also called Gram matrix, so therefore I use G to represent that. So you see this one is like GKI here, this becomes GIJ here, this becomes GKJ here. Then you see that this is actually just a matrix multiplication, right? Of G multiplied by G again, and then multiplied by alpha, something like that. And similarly, this one is just G multiplied by alpha. So therefore, we have this, and then we can cancel the G. Then it turns out it's something very nice that the alpha itself is actually, the weights there is just eigenvectors of G. So we know how to compute the Gram matrix, and that from that we can compute eigenvector, and that we can in terms compute the eigenvector for in the free space. But of course, that is actually not, even you have this, one thing like I guess I should emphasize, even I have this alpha here, I have this alpha here, this is not computable because I have this phi here. So, but That's actually still one more thing like we mentioned last time is like we always assume that like in the high dimensional is half center, right? So in the sense like we during the whole discussion we always assume this like all the vectors like basically zero mean. So we assume it's like equal to 0. Or like for the kernel case, we assume like phi x is equal to 0 is 0 mean. So it may not be true in general. So what we can do is like we can replace like phi xi by this guy here. So if you expand that out, you'll find that essentially it's just replacing like G, the grand matrix, by this one instead. So I guess that's the summary. A quick summary for kernel PCA is that you you determine a kernel first, and then like after you design the kernel, then you because based on the kernel you compute the grand matrix, right? Then you need to normalize that grand matrix using this to normalize that. Then afterward you can decompose the grand matrix, you get the eigenvector, then you can generate the alphas there. And then like if you have a new input, you cannot directly compute the eigenvector. So as I mentioned, that you cannot directly compute this. For example, like v equal to alpha I phi k phi xi, let's say. But if I have a new input, I can compute the projection, right? The projection, for example, I project to some new vector input x. So therefore, I'm interested to look at, for example, phi x v. Then I will have this phi x phi xi, the inner product of this guy. So this again will become the kernel. That this is something I can compute. So it looks nice, and I try to play a bit more like in the weekend. Then typically like when you start to look at something, then like the more you realize that something is not you do not completely understand everything. Then I find people like, okay, a good use of this is trying to denoise using kernel PC, so I guess I show some result like here. Let's see if I can find it. Yeah, actually interesting. It did compare with some autoencoder, so if like different number of like bases is kept basically. So the denoising idea is very simple, right? So if you project to basically you look at all the principal component and see how the just sorted in from in descending order. So you will keep the first maybe 10, 20, so like in this case keep the first 4 or 16 or something like that. So this is the classic PCA. So you just keep like 4, 16 and so on. You keep more. So up here, like when you keep too many, then like you starting to getting noise and so on. So the kernel PCA is quite a bit better. So but actually there's I would say there's still something like a remark. Oh, where's my? So for classic PCA, it's kind of simple, right? You just discard the component, you keep the remaining one. So, but in kernel PCA, what's the problem for kernel PCA? Actually, do you already foresee that the problem there? Actually, I'm writing the solution here, writing the answer here, but I don't know. So let's say, just like PCA, right, we in the fine space, in the high dimensional space, we keep like k principal components here and discard the rest, right? So then Vk is like the eigenvectors in those high dimensional space, right? So if I have fine x here, so basically I will just project to all this like V1 up to Vk here, and only keep that projection, and then the rest I won't remain there, right? But the problem is I need to, this is the projection, right, in the high dimensional space. So actually I need to find the input, or like find my estimate that actually will project to that, like in the fine space where I satisfy equal to, I will be equal to this guy here, right? So, and of course it's not immediately obvious, then the easiest thing is just trying to do optimization, right? I will try to say if I have a C here and just want to minimize this guy here. So this is like in the fine space, basically, like this is like after we discard like all the smaller components, like from k plus 1 m up, and we just want to minimize this guy here. So then we can expand this. This is not difficult because, okay, this is not a constraint optimization problem, so we can just expand that. And note that we only are optimizing over C, right? So then like some of the variables we can discard that. So we only keep the variable in terms of C here. And I'm also like, when I write like this, like basically like find C, I get like this kernel over C. So here I will just assume a special kernel. Basically, if I assume, for example, the Gaussian kernel, then have form like this kind of kernel, then kcc is just a constant, right? So cc here, this just cancel, so it's just equal to a constant. So therefore, this won't be important. So eventually, it will be just equal to kind of like maximizing this guy. And then you can take gradient and so on, and essentially you will have a solution like this. I just want to say, like, this is research, basically. Like, when you do research with something like that, like you take a problem and then you try to figure out like what's going on, then you work on a little bit, and then only when you start working on that you realize that not complete all the things you understand. So for example, like, okay, I look until that, okay, everything seems okay, and I think I'm done here, basically. But when I try to implement that, like, then I realize there's another problem. So basically, like, I think here briefly mentioned that, like, you don't we don't have we don't necessarily have like find is normalized, right? So in the kernel matrix, we can kind of normalize the kernel matrix somehow. So this can be done. Then I have this kernel matrix. So I essentially I able to find a normalized value of like, let's say x1 or like some training vector like xi and xj. So I can figure out the value for that by doing this normalization here. But now then, like, if I have a new vector here, xi, then it's all not obvious that, like, how this will be normalized actually. Because this is normalized in the sense like this g here. Actually, I have this g again. It's basically I have training vector x1 up to xn here, and I compute the entire kernel matrix as a k x1 x1 and so on, the entire matrix, and then I just column wise and row wise subtract the mean. Basically, that's basically, it looks complicated, but it's basically just what it did. It row wise subtract the mean, compute the mean along the columns, compute the means along the row, then you subtract that. But now you have a new input here, like x, and then you just try to compute this with some, let's say, training vectors, and compute the kernel of that. And of course, if I don't do this normalization, this will be like totally off, right? So I see you guys are not quite interested, but I don't know. So, but I don't know, seriously, like you only when you dig deep you will get something out of something, like and oftentimes it doesn't matter like what you are digging actually, For example, like a couple years ago, all this optimization technique, now I forgot. Like there's several of them, like from those Stanford guy. Like basically, what he did is just taking like lots of paper and saying, okay, this is the optimization method, and many people don't understand that. And actually, it has been introduced in the 70s or something, but no one actually uses it. And now I'm teaching you that this is exactly what's going on and apply in many other areas and so on. And I would say like sometimes this in the deep learning stuff, also some areas, for example, autoencoder, like denoising autoencoder, stuff like that, like also have more or variation of autoencoder, use lots of like classic stats thing and kind of combine them together. So I know it's not immediately seem useful, but that I think it's useful in the sense that if you have a strong background, then you will be able to combine to lots of stuff. And if you're only tracing the newest thing at this moment, like a fashion with like shallow understanding, actually you probably cannot do much. Like so. And here, I honestly, as I mentioned, this question here, I don't have an answer yet. So for the moment, that's what I did. Some tests is like, okay, I will just do similar what I did here. Basically, I would subtract the column. Subtract the mean, do a column wise and row wise subtraction. In this case, I will just do I only have 1D essentially here because I only have one x here, so I only can do a 1D subtracting the mean. I don't know whether it's a correct way to do it, but I try to do it, kind of like play a little bit. I mean, outside this thing, sometimes it's like kind of impressive. Like this guy, for example, like it denoise really well, but it have this shadow, like it's not clear. I'm not sure. Maybe it's because the way I do this. Let me try another sample, see if I to make any difference. Okay, this, but somehow I have a very strong this thing here. Of course, if I look at the paper, you're not using the same set of data. It's using data. I don't know what kind of data they use because it's here I'm basically just using M this way, and if I use M this here, the dimensions are a little bit bigger than what they have. So apparently I have a very weird shadow like circle here for some reason. Maybe I should decrease the number of bases here. Maybe let's see. This does not look good also. Oh, I don't know. Why it's so bad. Like I think like I have some. This looks pretty much have. Anyway, like I did it like in a wash, so maybe there's some bug, but that I haven't figured that out. But just outside that it looks pretty well denoised, but.
What is different between two? Like the second one is very clear.
No, the second one is the original actually.
Oh.
It's the noisy one.
Which one?
Yeah. Here is outside is actually denoised. Like somehow I got a shadow here. I have no idea like why I have a shadow here actually. I have certain suspicions that it could be bug, but I didn't have enough time to play with that, so. But anyway, like I guess I elaborate a bit far, digress a little bit far, but I think kernel check is cool. Like it's kind of important, and so therefore, like I like to talk a bit about that. But then last time I think I was a bit rushed, therefore like to back. So any questions? I guess I won't. Next time we'll be really starting to have like neural network. But I guess
What's the point of using kernel PCA instead of just PCA? PCA seems much easier to implement.
The result is better also, as you can see. So because you can project to a high. Okay, I guess maybe like the early. I will show you like that one also. Maybe I have that. If I show the early here. So for example, if you have data like this, like PCA won't do anything, right? So it's basically it's like separable. Like this is like a 2D data already.
Mm-hmm.
But you look at like what's that? Yeah, basically you won't do anything. So, but if you project to high dimension, then this can be separable. Actually, like this is kind of a result from kernel PCA. It's not completely separable, but this software is separable. So it basically project to here. I project to a very high dimension.
So PCA is dimensionality reduction, and kernel PCA is increasing the dimensionality.
It depends how you can still like increase the dimension and then you reduce that way. But for example, if you start with your data, if you want to do some denoising, like if your data is already in low dimension, there's no way you can PCA you cannot remove any more components, right? But then you can project to higher dimension, right? You start with maybe 10 dimensions. Then if you want to denoising, I cannot remove more dimensions. I can remove 1, 2, or maybe it doesn't do anything. But I can do kernel PCA first project to like 300 dimensions. then I remove like 290 dimension, and then I will have some denoising effect there.
So wouldn't that have the same effect of just projecting to a higher dimension first and then running just regular PCA?
You cannot. The problem is like, oftentimes you don't know how. Okay, oftentimes when I say project to higher dimension, it's like much higher dimension, right? And okay, for when you project to higher dimension, like how do you project is like a question, right? In the sense of how do we design that fine? So the kernel trick is always like, I don't know what is the fine supposed to be, but I know what is like the inner product of like two fine vectors. So what I mean is like, again, like, I don't exactly know what is this. This is not even know like what should I do with that, but I can design stuff like this. And I'm easy to find a lot of like function that have nice property for this guy, this kernel function. Yeah. And
So you're saying that
yeah.
the projection is just so many dimensions, it's easier just to use the kernel function?
It's not just that like that. Like how do you create a kernel? How do you create a fine? You don't know how to create this fine actually. For example, like if you are doing like Gaussian kernels, this kind of kernel, like so essentially, like you can kind of show that like this is actually the fine will be an infinite dimension. It's basically project to an infinite dimensional space. Yeah. So there's no way you can write it out. Yeah.
That makes sense.
Yeah. So, yeah, I don't know. Like, yeah, this is cool. Like, probably like can apply somewhere. Like maybe several years later, suddenly have like a kernel for deep learning combined whatever stuff like that. And, any other questions? So if not, I guess we will just stop here. So, and I didn't, yeah, I guess next time we will decide the schedule of our presentation. So we start, anyway, like your earliest presentation will be like March 10, but let's determine that like next time, like the exact order.
Do we need to send the topic to?
Yeah, I think like you better decide the topics maybe like how about by 22nd or something like that.
February 22nd.
Yeah.
How can we send this topic through Pizza?
I will put okay. I think you guys can discuss that in Piazza. Actually, it's a good idea to do that. Like, yeah, and then like maybe I will set it as an assignment. I'm setting in Canvas, so then you guys will have hard deadline. Otherwise, yeah. So, okay, so I guess I will just stop here.